All right, so here we go. 9.2 tests about a population proportion. All right, here are our conditions that we need to check before we perform a significance test about a proportion. These are the same as when we conducted them for a confidence interval. One slight difference. Note that what you're checking is n times p naught. This is the p-value that comes from your null hypothesis. Remember, the null hypothesis is what we assume to be true. Okay? So it's not your sample p anymore. This is actually the p-value that you assume to be true from the null hypothesis. Everything else is the exact same, and these are just checking a box, right? Getting points. Okay. So let's just practice that in the context of an actual problem. According to the US Census Bureau, the proportion of students in high school who have a part-time job is 0.25. An administrator at a local high school suspects that the proportion of students at her school who have a part-time job is less than the national figure. She'd like to carry out a test at the alpha equals 0.05 significance level. And then here we have our null hypothesis, which is that the proportion at her school is the same as the national level. It's 0.25. And then the alternative that she's looking for evidence of would be that the p is less than 0.25. The administrator selects a random sample of 200 students from the school and finds that 39 of them have a part-time job. Check if the conditions for performing a significance test are met. So 39 out of 200 is 0.195. So the p hat she gets from her sample is 0.195. So there's at least evidence in her sample that her alternative hypothesis might be true, right? All right, all they want us to do here is check conditions. Random. So that's our first condition. It's stated as a random sample. Good. 10%. For this one, just multiply your sample size by 10. So 10 times 200 is 2,000. And it doesn't say anything about the population of the school, but we'll just assume the school's population. You can refer to any population that of interest as capital N is greater than 2,000, which would not be true of our high school, but many large high schools are more than 2,000 kids. All right. And then large counts. So here's where it would be slightly different. We're not going to use our p hat value. What we're going to use is the assumed value from the null hypothesis for p. So 0.25 times 200 is 50, which is greater than 10, right? And then do the complement of that. 0.75 times 200 is 150, which is also greater than 10. All right, and that's it. We've checked all our conditions. This is something that's obnoxious but necessary, and you just need to be in the habit of doing it. All right. So I'm going to jump through this one. We'll do an example of this, but this is just justifying that if the conditions are met, then here's what we can expect for the sampling distribution that we're studying, right? It should center over the assumed value, 0.8, and in this case, and it will have standard deviation based on our standard deviation formula, where we'll use our p naught value again in place of p hat. All right. So we're going to take the same problem and we're going to calculate what we call a p-value. A p-value is a conditional probability. So we talked about this last time, but a p-value is the probability that you get your p hat or more extreme in the direction of the alternative hypothesis, given that the null hypothesis is true. And so this will make more sense once we have some context here. All right, so this is the exact same problem we just did. Part A says explain why the sample result gives some evidence for the alternative hypothesis. So the result that this administrator got was that 39 out of 200 students had a job. If you do 39 divided by 200, that gives you, what did I say, 0.195. Why does that give evidence of the alternative? Exactly. So p hat is less than the assumed p naught, right? So since our sample is less than 0.25, which is what the alternative is stating, we do have some evidence of that. All right, so calculate the standardized test statistic. So a standardized test statistic is really just a z-score. So it's the statistic minus parameter divided by standard deviation of the statistic. So I'm going to do, for part B, my standardized test statistic will be p hat minus p naught divided by the standard deviation, which is going to be p naught times 1 minus p naught divided by n. All right, so for us that comes out to 0.195 minus 0.25 divided by root 0.25 times 0.75 over 200. All right, so I'll pop that in the calculator. All right, and I get about negative 1.796. All All right, so we're going to calculate a p-value. I'm going to kind of do it by hand. And when I say by hand, I don't really mean by hand. I mean in our calculator, but we're sort of breaking this down into steps when the reality is we could just run this whole test in our calculator. It could do all of these parts for us. But I want to understand what we're looking at. So here's what we assumed. We assumed that the null hypothesis is true, which means our sampling distribution should have a center at 0.25, right? Now, we got a sample that was less than that. Our sample was way over here. It's p hat, it was 0.195. And what we want to see is how likely is it that we would get that sample by random chance, or more extreme in the direction of the alternative hypothesis. So how likely is it that we would get 0.195 or less by random chance if the null hypothesis is true, if it truly centers over 0.25? If it's really unlikely, then we'll conclude, hey, I don't think this happened by chance. I think this happened because the alternative hypothesis is actually true. If it's not that unlikely, we'll go, I could have just gotten this sample by random chance, and I don't think I have enough evidence to conclude that the null hypothesis isn't true, okay? All right, so what I want to do is find that area. That is my p-value. And that's my probability that I get my sample if my null hypothesis is true. What I did just now is just convert it to a z-score so that now I can look at it in terms of the standard normal distribution. And so that's just the normal distribution that has a mean of 0 and a standard deviation of 1. And so if I want to do this in my calculator, all right. Make sure I share this with you, Maya. There you go. So here I would go to my distribution menu. I would do normal CDF. My lower boundary is negative infinity. My upper boundary is going to be that standardized test statistic that I got, which was negative 1.796. My mean is 0, my standard deviation is 1. There we go. I get a p-value of about 0.03. 0.04 if I round to 2 decimal places. So what would I conclude at the alpha equals 0.05 level? All right, so part C. At alpha equals 0.05, do we reject the null hypothesis or do we fail to reject the null hypothesis? Do we have enough evidence? Remember, alpha is your significance level. That's your threshold for making your decision. And we're making our decision based on how likely is it that we get a sample this extreme if the null hypothesis is true. The lower our p-value, the more evidence we have for the alternative hypothesis. Is this p-value low enough to conclude that we have enough evidence to reject the null hypothesis? Yeah, it's below alpha. So at alpha equals 0.05, we'll say we reject H null in favor of HA. So that's your first sentence. It's a 2-sentence conclusion. You just abstractly either reject the null hypothesis or fail to reject. The second sentence, you state it in context. We have sufficient evidence to support that, oh, I'm running out of room here, less than 0.25 students at this school work. Okay. So again, the logic is if 25% of students at that school did work, it's really unlikely that we would get a sample that low by random chance. It's unlikely enough to happen that we're saying, okay, that's enough evidence for us to say that I don't think 25% of students at the school work. I think less than 25% of the students at that school work, right? And your threshold for how unlikely that has to be is your alpha. If your p-value comes below that, you reject in favor of the alternative. If your p-value is above that, you fail to reject, meaning you don't have enough evidence to support your alternative. Now, let's go back to the calculator. We did that one by hand. We calculated that p-value, as I say, by hand, using normal CDF. You actually don't have to do that. Your calculator can run the full test for you, and that's 100% fine to do. Just, you need to name the test that you're using, just like we name the type of confidence interval that we're using when we use our calculator. All right, so here's where we can find the function to run a significance test for us. It's stat tests. And if it has prop, it's for a proportion. If it doesn't have prop, it's for a mean. We haven't done any confidence intervals or tests for means yet, so you're looking for a one prop z-test. The one meaning it's from a single sample. Prop meaning proportion. Z-test. Hit enter. It'll ask you for what's your p naught value. So for us, that was 0.25. And then it'll ask for x and n. So x over n should give you your sample proportion. So for us, that was 39 out of 200. And then it'll ask for the direction of your alternative hypothesis. So our alternative is less than. So I need to highlight that. And you can have it draw, it'll draw the distribution for you. Sorry, I have some other graph there. Some other stat plot turned on. Turned off, and I'll rerun it. All right. There we go. And it gives us that our p-value right there, and it gives us our test statistic that we had calculated by hand. So p-value is 0.0362. Test statistic is 1.7963. You can see shading the area that I shaded in our diagram. And that's it. Questions so far? All right, let's get to it. I think there are a couple more examples just so we get some practice in on this. All right, so just the four-step process. Again, this isn't something you have to do, but it just helps you organize your thinking so you make sure not to leave anything out on a free response question. State. In the state step, you'll state your hypotheses and the significance level. Define any parameter that you're going to use. Plan. Check conditions. Do. Perform the calculations. This you can do 100% in your calculator. Things that you want to make sure that you list are anything that your calculator spits out. So namely the z-test statistic and the p-value, right? And then conclude. Make a conclusion about the hypothesis. 2 sentences. First sentence, either you reject or you fail to reject the null hypothesis in favor of the alternative. Second sentence, give context to the situation. Okay. So there are three kinds of tests, three types of alternative hypotheses that you can find. You have that you think P is actually greater than P naught, and in that case, you'd be finding the area in the right tail. P is less than P naught. This is like the example we just did. You're finding the area in the left tail. Or not equal to P naught, you're actually finding the area in both tails. Okay, so this is going back to the problem that we talked about in 9.1, blemished potatoes. And they want us to conduct a significance test that more than 8% of the potatoes in the shipment have blemishes. And we're going to do this at the alpha equals 0.1 level. All right. So we have a sample size of 500 potatoes, and it says that 47 of them have blemishes. So we're going to go just full on through this. We need to send back the truckload of potatoes if more than 8% are blemished. So I'm going to go full on state plan do conclude here. So state, my parameter of interest is P, the true proportion of blemished potatoes. And then we're going to state our hypotheses. So you guys help me out with this. What should my null hypothesis be? P is what? What are we going to assume? Point what? I'm not saying you're wrong. Honestly, I didn't hear you. Yeah. So we'll assume it's exactly 0.08. That's our threshold for sending the truck back. But we're looking for evidence of what? What's our alternative? Yeah. We're looking for evidence that P is greater than 0.08. Remember, your null is always an equation. Your alternative is the same thing on the right and left-hand side, but it's going to be an inequality. All right. And so plan, let's check our conditions. Random. I'm just going to say stated as SRS. 10%, we'll assume the truck contains more than 5,000 potatoes. So that's just 10 times my sample size. All right, and then large counts, remember we use our null hypothesis, p-value. So it's going to be 500 times 0.08. 40, which is greater than 10. And clearly 500 times 0.92 is going to be 460, right? Which is also greater than 10. All right, so now we're on to the do step. We're going to conduct a one sample z-test for a proportion. My p-hat value is what? 47 out of 500. Which is 0.094. Does that support our alternative hypothesis? It does. It is greater than 8%, right? Now, just intuitively, is that a lot greater than 8%? If you have to guess, do you think that's going to give us enough evidence to support the alternative and say that this isn't likely to happen by random chance? No, that's called the effect size, like how different your sample is from your null hypothesis. The larger the effect size, the more likely you're going to have enough evidence to support your alternative, right? This is a pretty small effect size. But if our significance level is also pretty high. So at that significance level, maybe. But let's run the test and see. So in our calculator, let's go to our stat tests. We want, tests. We want the one prop z test, so the fifth option. Our p-value now is 0.08, or our p not value. Our x is 47. Sample size is 500. We want to change this to be greater than. All right, so copy down the test statistics. So z equals 1.1539. And our p-value is 0.1243. All right, so what's our conclusion here? Conclude. Do we reject the null hypothesis or do we fail to reject it? Our p-value is greater than alpha, right? It's larger than our significance level. So there's not enough evidence to say that this didn't just happen by random chance. So we fail to reject it. So I'm going to start with the significance level, sorry. At the alpha equals 0.1 level, we fail to reject H null in favor of HA. We don't have significant evidence that there are more than 8% blemished potatoes. All right, so that's a full-on significance test, start to finish, everything that you kind of need to include. Questions? So you're looking for small p-values. P-value needs to be smaller than alpha to be able to support the alternative hypothesis in a significant way, right? All right. Yeah, one thing, just a common mistake, and I think I've already sort of mentioned this, and it's just like, it's analogous to a criminal trial. You never have evidence that supports the null hypothesis, because the null hypothesis you're assuming to be true in the first place. You only have enough evidence to support the alternative, or you fail to have enough evidence to support the alternative. So you never want to say we accept the null hypothesis, just like it's never, right? The outcome in a court trial is never innocent. It's always guilty or not guilty because they're presumed innocent. All right. So let's talk about a two-sided test. And we're just going to do another problem. We'll do it all the way through. So according to the CDC website, 68% of high school students have never smoked a cigarette. Yan Hong wonders whether this national result holds true in her large urban high school. So for her AP statistics class project, she surveys a simple random sample of 150 students from her school. She gets responses from all 150, and 90 say they have never smoked a cigarette. Is there convincing evidence that the CDC's claim does not hold true at Yan Hong's school? All right. So Yan Hong doesn't wonder whether her school is greater than the national average or less than the national average. She only states that she wonders if it's different. Okay, so that indicates that our alternative hypothesis is going to be not equal to, and we're doing a two-sided test. So I'm just going to walk through this one fully again. So state P is the true proportion of students at Yan Hong's school who have not smoked. All right, folks, help me out here. What's my null hypothesis? H naught should be P is what? Yep, so we'll assume it's the exact same as the national average. And then as I said, my alternative, since she doesn't indicate a direction, is going to be not equal to, right? Great. They don't state a significance level, so we're just always, if it's not stated for you, default to the 0.05 level. And then I'll go plan. Everybody's favorite part, checking conditions. Random. And it's stated as an SRS. %. If I multiply her sample size by 10, I get 1,500, and we'll just say, assume capital N is greater than 1,500. Safe to assume a large urban school would have more than 1,500 students. And large counts is going to be 150 times 0.68. Which is 102, that's greater than 10. And then 150 times 0.32, which is 48, also greater than 10. Okay. So we're ready for do. We want a one sample z-test for proportions. All right, I'm going to pause here. All right, so for our do step, I'm going to tests. On my one prop z-test, the p-value is 0.68. Here, oh, what was it, 90 out of 150. 90 there, 150. And I need to change this to not equal to. All right, I get the same thing that Sam got. P is 0.0357. Great. So let's just go ahead and conclude. At alpha equals 0.05, we reject the null hypothesis, so H null in favor of HA. We do have sufficient evidence. We have sufficient evidence that the proportion of students have not smoked at Yanheng School is different from the national average. Whew. All right. So once you get this down, I mean, it's the same thing every time in terms of stating, checking conditions, drawing conclusions, right? It just takes a couple practice tries and then this becomes kind of second nature. And just making sure you're not being lazy and actually finishing your sentences and writing this out so you're getting full credit. All right, so there is a link between intervals and confidence intervals and two-sided tests. So a 95% confidence interval gives an approximate set of P naughts that should not be rejected by a two-sided test at the alpha equals 0.05 significance level. Any P naught value outside the interval should be rejected as implausible. Hold on. All right. This is a question from the 2005 AP Statistics Administration. So this is an example of what an FRQ will look like for you that involves a significance test. So I just want to have you guys go through and try this one. I'll read through it, and then I'm just going to let you go at it. Some boxes of a certain brand of breakfast cereal include a voucher for a free video rental inside the box. You can tell this is definitely from 2005. The company that makes the cereal claims the voucher can be found in 20% of the boxes. However, based on their experiences eating this cereal at home, a group of students believes that the proportion of boxes with vouchers is less than 0.2. This group of students purchased 65 boxes of cereal to investigate the company's claim, and the students found a total of 11 vouchers for free video rentals in the 65 boxes. Suppose it's reasonable to assume that the 65 boxes purchased by the students are a random sample of all boxes of this cereal. Based on the sample, is there support for the students' beliefs that the proportion with vouchers is less than 0.2 and provides statistical evidence to support your answer? All right, let's take 5 minutes. I want you to fully write this out as if it were on the test and come up with a conclusion. And then we'll check your answers. Riley, what'd you get for the null and alternative hypotheses? Perfect. I'm not going to make you guys verbally check conditions for me. That's just something you're going to need to be doing, but I'll put that up on the board in a second. Steffi, what did you get? Did you run the test in your calculator? Okay. Does anybody have the p-value? Go ahead, Sam.
P equals 0.73.
You got 0.73? Yeah, I got 0.26 as well. Make sure that your hypothesis is going in the right direction. It should be less than. You might have done greater than on accident since it's the complement of what we got. I agree, 0.26, 0.2676. All right, so Kaylee, what should our conclusion be? Okay. Oh, the level? So that's just, alpha is, that's our cutoff, basically, for where our p-value needs to be. If our p-value is above alpha, we fail to reject. If our p-value is below alpha, we reject the null hypothesis in favor of the alternative. So it's just good practice in your conclusion to state what significance level you're using to make your decision on whether you reject or fail to reject. So in this case, at alpha equals 0.05, what are we doing? Rejecting or failing to reject? If it's above, you fail to reject. Yeah, so what we're saying is it's highly unlikely we fail to reject the null hypothesis. We're saying it's not unlikely enough that we wouldn't have got this by random chance. Let me restate that because that was about a quadruple negative. We're looking for evidence that this is unlikely to have occurred randomly if the null hypothesis is true. You can see that our sample here, 11 into 65 is what? 11 divided by 65 is about 16.9%. So our p-hat value, although it does support the alternative, the effect size isn't large enough to go, hey, our p-hat is lower than the p-naught value, therefore I think the p-naught value is not correct. Does that make sense? So this could have just, we could have just gotten this sample randomly and the null hypothesis is still true, right? Right. Okay. Sorry, it's 0.619, not 16.9. 0.169. All right. So again, that's called effect size. How different is your sample from the assumed null hypothesis? And our sample is different, right? There is evidence of the alternative there. There's just not enough evidence for us to say that this couldn't have occurred just by sampling variability. But the bigger the effect size, the more evidence you have, right? So last thing we're going to talk about is going to go back to type 1 and type 2 error. Remember, type 1 error is a false positive. Type 2 error is a false negative. What type of error could we have committed here? So we failed to reject. Is that a negative result or a positive result? Negative. Positive would be having enough evidence to reject. So we failed to reject. So we're going to consider that a negative result, right, on the test. So we could have committed, we may have committed a type 2. Okay? And if we did, that means that really this cereal company is gaming the system. They're claiming to put 20% of the boxes with video rental vouchers, but they're actually filling less than 20% with video rental vouchers. In which case, we should have rejected the null hypothesis, right? So that would have been a type 2 error. So that's linked to this thing called the power of a test. So researchers often perform a significance test in hopes of finding convincing evidence for the alternative hypothesis. And we could make a type 2 error if we failed to find convincing evidence based on the sample data, when in reality we should have rejected the null hypothesis. So how likely is a significance test to avoid a type 2 error? We refer to that probability as the power of the test to reject the null hypothesis. Okay, so this is a definition you need. The power of a test is the probability that the test will find convincing evidence for the alternative when a specific alternative value of the parameter is true. So I want to give you this in context. In our last example, okay, what if I'm the owner of this cereal company and I am a dirty trickster and I'm actually only filling 18% of the boxes with vouchers, but I'm advertising to everybody. So I guess the Arizona Gaming Commission, I'm telling them that I'm filling 20% with vouchers. How likely is our test to find convincing evidence if only 18% are filled? It's not super likely, and that's because the effect size is so small, right? 18 is not very far from 20. So it's going to be really hard to get a sample that helps us prove that this is true. Like we said, we got a sample where only 16.9% had vouchers in them, but we still didn't reject the null hypothesis in that case, right? All right, well, what if I got greedy and I go, okay, well, now I'm going to start filling my only 10% of them. Is that going to be more, is our test more likely to find that the alternative is true or less likely, do you think? More likely, right? It's a larger effect size, so it's easier for the test to determine. That is really all I need you to know about the power of a test. It's how likely is your test to correctly reject the null hypothesis, okay? Given a specific alternative to be true. Usually, every other year, I'll go through and hand calculate the power of a test, even though you won't have to do that on the AP exam. But for this year, I'm not going to do that just for the sake of time. All you have to know is what power is and when power is increased. All right, the other thing I need you to know is that power is related to a type 2 error. The probability of committing a type 2 error is 1 minus the power. So write down what I circled in red. The probability of committing a type 2 error is 1 minus the power of the test. The only thing you'll ever be asked to do is either find the probability of a type 2 error, in which case I will give you the power. You just do 1 minus that and tell me that that's the probability of the type 2 error, or you'll be asked to interpret the power of a test. And so if you want to interpret the power of a test, here's an example. We did this example about the lifespan of batteries, where we were conducting a test to say the mean lifespan is 30 hours and the alternative is that it's greater than 30 hours. So here they say the power of the test to detect that, let's pretend the true mean battery life is 31 hours. So it's not a very large effect size. The power of the test to detect that will be 0.762. What that means is that in 76.2% of samples, we will have evidence to correctly reject H null in favor of HA. So that's how we interpret power. All that means is that, okay, if the true mean battery life is 31 hours, then about 76.2% of the time I'm going to get a sample that correctly tells me to reject the null hypothesis in favor of the alternative. The other about 24% of the time, I'm going to get a sample that tells me not to reject the null hypothesis, which is incorrect, and I'm going to commit a type 2 error, okay? All right, so how can we increase the power of a test? There are two ways to do it. You can get a larger sample size. A larger sample size gives you more information, making it more likely for you to find evidence and correctly reject the null hypothesis. Or when the effect size is larger, so, oh, sorry, that's the third bullet point. The other thing you can do is increase alpha, because when you increase alpha, that makes it easier to reject the null hypothesis, right? But that's going to increase the probability that you make a type 1 error. Remember, there's that trade-off between type 1 and type 2. Or if your effect size is larger, meaning the null and alternative parameter are farther apart. Okay. And we will stop there for today.